Hi, my name is Harry Zhang, and today I will be presenting the symmetries in the Standard Model. So first, we should explain what a symmetry is in physics. In physics, symmetries are transformations that preserve the results and outcomes of all experiments. Essentially, they keep the laws of physics the same. Historically, physicists have believed in three discrete symmetries: charge conjugation symmetry, parity symmetry, and time reversal symmetry. However, in the late 20th century, it was discovered that all three of these symmetries were broken. It seems that whenever the universe does not need to keep a symmetry, it chooses to break it, and breaks it in a way that is extremely subtle and difficult to detect unless being done by the most advanced physics experiments. These symmetries are important because breaking symmetry can solve a lot of unsolved problems in physics. For example, when physicists believed that matter and antimatter were symmetric, they had a difficult time explaining why there was so much more matter than antimatter in the universe. This is one example of how symmetry breaking can throw away old paradigms and introduce new pathways in physics. The first symmetry is parity symmetry. This is the sort of symmetry you see in mirrors. It's a left-right reversal. For a long time, physicists thought that the universe didn't distinguish between left and right, and that a mirror-symmetric universe would have every experiment have the exact same outcome. That was until in 1956, when American physicist Qian-Sheng Wu worked with the low-temperature group to perform an experiment with cobalt-60 nuclei. They placed cobalt-60 nuclei in a strong magnetic field and observed its beta decay. They found that the electrons emitted by the nuclei were preferentially emitted in a direction opposite to that of the magnetic field. This allows physicists to distinguish between north and south magnetic fields, and thus distinguish between left and right by analyzing the direction the wire curls to produce those magnetic fields. The next type of symmetry is charge symmetry. This is the symmetry between matter and antimatter. It was first indirectly broken in 1957 by Richard Garwick, an American physicist who discovered the hydrogen bomb. By analyzing the decay of certain particles, they found that they decayed into separate particles in a way that was not possible if charge conservation symmetry was true. However, it would not be until 1964 when Cronin and Fitch, two particle physicists who were awarded the Nobel Prize for their work, that charge conjugation symmetry would be definitively disproven. They analyzed how kaons decay into antiparticles and found that they decay into their antiparticles at differing rates. The process in which a kaon becomes its antiparticle is slightly faster than the process by which the antiparticle goes back into the kaon matter particle. This disproved charge conjugation symmetry, which left one symmetry: time reversal symmetry. Time reversal symmetry is the idea that the universe can tell the difference between the forward flow of time and the backward flow of time. Now, it may seem obvious to us that there's a direction to the flow of time in the universe. After all, we can always tell when a video is being played forward versus when a video is being played backwards. But this is different than what physicists consider to be the microscopic arrow of time. Physicists searched for a particle interaction which was distinguishable forwards and backwards. It was not until 2002 when a group of 500 scientists collaborated on the Babar experiment that a direct evidence of time reversal symmetry violation was found. They analyzed the oscillation of the B meson between its matter and antimatter form and found that the oscillation was asymmetric. It was slightly faster going to its matter form versus its antimatter form. Now, you may have seen those last two experiments and thought that they were very similar. They both involve particles oscillating between their antimatter and matter forms at different rates. That's because there's a third symmetry which the universe does appear to respect, which is CPT symmetry. It's a combination of all three previous types of symmetries, where if you reverse charge, reverse parity, and make time flow backwards, the outcomes of all experiments should stay the same. Wolfgang Pauli first demonstrated this symmetry in a book dedicated to development of physics, published in 1955. By combining the basic assumptions of special relativity and quantum mechanics, he proved that CPT symmetry must be true. Since then, many physicists have attempted to conduct experiments disproving CPT symmetry, because if CPT symmetry were to be disproven, it would show that our fundamental assumptions of quantum mechanics and special relativity are not true. But to this day, no physicist has performed an experiment which definitively violates CPT symmetry. Thank you for coming to my presentation today. Brace.